All right, so let's get started with a quick recap of what we did last time. Okay, so we try to solve this linear system with three equations and three variables using Gaussian elimination. But it would be better to understand it in terms of like using matrices. So let me try to write it in another way using a metric form. Okay, so the way we would do that is like we would represent the whole thing as the matrix. Okay, first of all, this part, okay, has three numbers, right? So we would basically write them as a vector. Okay, you think of a vector. We haven't defined it yet, but assume that we try to understand it by looking at this example first. So a vector is basically an order list of numbers. Okay, so we write it this way. So three numbers and you have a vector of length 3. Okay, here we just started by extracting all the coefficients of each variable. Okay, so we would have something like, but this matrix alone, only contain coefficients, right? We don't really have variable yet, so we need to add it here: x1, x2, x3. This equals to this. Okay, so if you look at the format, it looks pretty much the same as the both. Okay, but why is that? Because the way we write, the way we do metric multiplications. Okay, I'll come back with that soon, and to see like various way of viewing matrix vector multiplication. So we have a matrix here, and this is a vector. Okay, so you can see this as a metric vector multiplication. Okay, but for now you can think of this as you have the first row here, right? The first row get multiplied with these columns, and you obtain 7. Okay, the way you do the multiplication here is basically you do it element wise. So the first element here get multiplied with the first element in the column. Okay, and then you multiply 4 with x2 and 3 with x3, and you add them up. Okay, so basically after this multiplication, you essentially obtain this value. Okay, and it says that it's 7. Okay, so the other rows can be obtained in the same way. Okay, so you multiply 1 with x1, 0 with x2, and 5 with x3, and you get 12. Okay, and finally 4 with x1, like this guy, 2 with x2, and you get this, and 3 with x3, get this, and equals to 10. Okay, so this is how we explain the way we write it as a matrix. Okay, now I will show you what we did during the Gaussian elimination process, but we'll look entirely at this matrix. All right. Okay, the coefficient here is important as well, but not that much, so we will probably ignore it for now. Okay, all right, so let's see what we did with this. All right, so we start with this matrix. Okay, and then we would like to sort of like our plan is to eliminate like this and this. Okay, so that we only have x1 appear in just one equation. Okay, if we can continue to doing that, like so let's try to do this first. Okay, so we try to eliminate x1 from all the other equation. Okay, it'll be much easier if we have 1 here, because it's easy to deal with 1. So what I did was just do this. So basically I divide this row by 2, right? So I divide 1 by 2, right? So I get 1, 2, and 1.5. Okay, and then what's next is that what I did is I subtract the second row, right? Second row got subtract by second row minus the first row. Okay, what I get is this, the first row remain the same, second row this becomes 0, this is minus 2, and this is 3.5. okay, and then 4, 2, 3, that. Okay, and then the next step is like I multiply the whole thing by 4 and subtract this. Okay, so then I get row 3 to be row 3 minus 4r1. Okay, I get the first row remain the same, second row remain the same, and then the third row this becomes 0, and then I multiply this by 4, right? So I get 8, so this is minus 6, and this is like 6 as well, so this is minus 3. Okay, again, it will be easier for me to have 1 here, right? Because if I have 1 here, I can eliminate. My goal is to eliminate this guy. Okay, so I would do this. I would multiply, I would say R2 equals R2 over minus 2. I divide the whole thing by minus 2. Okay, so what I would get is 1. The first row remain the same, second row is 0, this is 1. I divide this by minus 2, right? So I get 1.75, right? Minus, okay, and then this is minus 6, this is minus 3, it's remain the same. Okay, so the last step, I would just take the third row and subtract it with add it with 6 times row 2, right? So what I would get is the first 2 rows remain the same, the second rows, and then I multiply the whole thing by 6, right? And I add it, so this becomes 0, this will be 0 as well, and finally I have minus 3, right? So let me have a note here, and then I do 6 times 1.75, so I get minus 10.5. Okay, so this is my matrices. Okay, so if you want to really solve this, you need to carry this column around as well, but in the end we have something that look like this. Okay, this is what we call a triangular matrix. Okay, so because we have the 0 here, so this becomes 0, and then these are non-zero. Okay, matrices like this are nice when you want to solve a linear equation, because we can basically what we would do is like if we carry this column around and also calculate, do everything with it. Okay, so you so in the end you have some the coefficient here as well, right? But let's ignore it for now. If you want to find the value of the variables, we can do the substitution method. Okay, we can basically because there's already one variable here, so you can definitely find a value for it. Okay, after that we substitute in here, and then this equation only have one variable left, right? So when you have one variable left in an equation, you can solve it, so you can now you have its value. And finally you have this, the value of these two variables, x2, x3, right? And you substitute into the first equation, and then you can solve the last variable. So when we have a matrix like this, it's really nice, it's really good for us. Okay, so this is what we did in terms of matrix. Okay, so now let's look at another example in this way as well. Okay, so this is another example. So let me write the matrix first. Okay, so it's 2. Just look at the coefficient matrix for now. It's 1, 0, 5. Finally 3, 8, 1. Okay, now I can do the same by dividing the first row by 2, right? So I get 1, 2, 1.5, and 1, 0, 5. Okay, so I say 1 equals 1 by 2. Okay. Okay, the next step is roughly the same, so I will do that really quickly. So I subtract the second row with the first row. Okay, so I get the first row being the same. Second row is 0, minus 2, and 3.5. Okay, and the last row remain the same. Okay, now it will get more interesting here after this. So I have R3 minus 3R1. Okay, so what do we get here? 1, 2, 1.5, 0, minus 2, 3.5. Now, this becomes 0. Okay, so I have 2 times 3, subtract with this, so I have remain 2, right? And here I multiply by 3, so I get 4.5 minus 1, so I get. Okay, now you can see that this row are pretty much the same, right? So it's like, so this row is basically R2 times minus 1. Okay, so if you continue to do the Gaussian elimination as we did, now I will skip the step when I normalize this to 1. Okay, I'll just do I just want to get the point across. So I say R3 equals R3 plus R2. What you would get is something like 1, 2, 1.5, 0, minus 2. And then I have 0 here. Okay. Now, this kind of metric is also nice. Not that nice, but it's also nice. Because when we have a row like this, we know that the row is sort of like meaningless, right? Okay. Now, again, if we really want to solve this equation, this system equation, we need to maintain this this value, this constant. And if we do it when we do the row operation, we need to maintain perform the row operation on this column as well. And if we actually maintain that, we will see that in the end, this the value of the last value in the vector will become non-zero for this exact system of linear equation. When this happens, we know that the system doesn't have a solution, because okay, you have 0 here, but you want it to be non-zero. Okay, so you have a 0, 0, and this is non-zero, and you want 0 to be non-zero. That's impossible, right? So you know that there's no answer for it. Okay, but however, if I change this to as I told you before, to 2, okay, and if you keep all this, then you have after you change it to 2, you have that this becomes 0 as well. So you have some equation that say something 0 equals 0. So this is like, it's okay, it's an okay equation. It's not impossible to satisfy it, but it's just automatically satisfied. You say 0 equals 0, so it's sort of like meaningless equation. So we end up with a system with 3 variables. Okay, 3 variables, but 2 equations. So can you solve it? Definitely yes. You can just basically set some of the variable here, because you have more variables than equation. In this case, you can say I would set x3 to be something, and then now I can solve for x2, and after I get x3 and x2, I can plug it into in this equation, and I can solve for x1. Okay, now you can solve it. Okay, but everything depends on the value of that you set for x3 here. So we'll see more on that later on. Okay, but in this case, if you have 0 equals 0, then it's okay. We can actually solve the equation, but the equation will have more than one solutions. Okay, so 3 cases again. This has one solution. Okay, because there's only one way to satisfy three equations at the same time like this. Okay, the other one, this one, when we haven't changed this to 2, it has no solution. And finally, the last one, when we change the constant here to 2, so it has many solutions. Okay, infinitely many. Okay, because we can pick one variable and set it to whatever we like. The other variable will follow. Okay, so basically they will have many solutions. When you plot it into the GeoGebra, so let me show you quickly how it looks in GeoGebra. Okay, here I draw all the equation as a plane, right? You can see that I have 3 equations, and somehow the third equation is if you look at this, it's in parallel, right? So there's no intersecting point, because the third equation is roughly it's the intersection between the two of the planes is a line, and they are all in parallel. You can see there's no intersection anywhere because it's completely parallel. Okay, so this is the case when there's no solution. Okay, now if I change this to 2, so let's take a look at that. You can see that this orange plane move a little bit, and then it basically touch the other plane, right? And you can see the intersection becomes a line. Okay, so that's this line here, you can see my pointer, right? This line here represent the set of solutions. Okay, again, when you see a line, don't think of it as a line. It's a set. Okay, the set of equation. So there are infinitely many solutions, and it follows this line. So the reason for that is that this this orange equation is sort of like meaningless, right? When we see that when we do Gaussian elimination, we obtain 0 equals 0, right? So it doesn't add to us any meaningful constraint. Okay, so this is the case when there are that many solutions. Okay, but if I change this a little bit, okay, so I do that. Okay, so if I change this to 2, you can see that now my equation has a solution, but not around here. So let's change this a little. Okay, all right, if I change it a little bit, you can see that there's some intersection here around this point. Okay, so they are not in parallel anymore, right? If I change it, you can see there's an intersection here. Maybe it's really small, but I hope you can see it somehow. Okay, so that's the case when we have only exactly one solution. Okay, all right, so I hope this gives you a quick review. All right, so before I show you another perspective to look at a set of linear equations, let's go back a little bit to see what we've just done. Okay, so this first perspective is basically focused on each row. So each row is a constraint, right? So this is a constraint. Okay, and then you add some of the constraint to obtain a new one. Okay, so basically we can look at them like this. When we obtain the third equation, we can look at like the first equation, we can just look at this coefficient, and the second equation we can look at its coefficients, and we can write them as a vector like this. Okay, to obtain the third equation. So this is like when we have 2 variables. Let's focus on the case when we have 2 variables first. Okay, so we basically do this subtract, right? So we subtract the first one with 3 times the second rows, and we obtain this. Okay, and then this is what we always do. Okay, so this is what we call a linear combination. So this thing, we will have a more formal definition on it soon, but the way we take a vector, multiply it with something, and do some addition and subtraction, we obtain a new vector. That new vector is called a linear combination of the first 2. Okay, all right, so when we do that with the matrices, like during this one, right? So this is the this row it's a linear combination of the first row, right? We multiply it by something, right? And then we do something like this. So this row is a result of sum of the, we multiply it with this row and then subtract, right? So this row is also a linear combination of the other two rows. And also the last row as well. So it's a linear combination of the other rows, right? If you look at all the operation that we did here, we can see that all the rows are linear combination of the original rows. Okay, so when we do Gaussian elimination, we build new rows, and these rows are the result of adding, subtracting, or multiplying some of the previous rows. So all the rows that we created are linear combinations of the rows, of the original rows. Okay, let's get back. So now when we have this, can you obtain 0, 1 from this vector by doing some multiplication or subtraction? Definitely yes. You can divide the whole thing by 25, right? So to obtain this, the other thing, you can just do that to get 0, 1. Okay, maybe I did something wrong here. So this should be 5, sorry. Okay, so if you want to get 0, 1 from this, I can just divide the whole thing by 5, right? And you can come back to look at the original vectors. So if you divide all the thing by 5, so this is like multiply by 0.2, and this is like subtract u1, and you get 0, 1. Okay, right? So you can actually obtain any vector from u1 and u2 as well. Okay, we'll come back to this point later. All right, in the next video, I will show you how to look at this in using the column perspective.